Coming up in this episode, why Conway's Game of Life is a great project for learning software engineering. Welcome to the first video in the Game of Life in Python series. This is going to be a software engineering series using Python, FastAPI server, Next.js for web UI, some client-side JavaScript, a bit of CSS, and we'll also go into WebSockets and microservices. All of this will be interweaved into our architecture and progressively improved as we go from simple to more complex. Now, if you do not know what S.O.L.I.D or design patterns are, then I would recommend researching that a bit, as that would help you in understanding the architectural decisions made in these videos. I do have a course which acts as a great introduction to all the concepts mentioned here, and I'll link it in the description. But it is not required to enjoy and benefit from this series. And of course, you're always welcome to ask questions here. So in this series, we're going to build Conway's Game of Life, but we're going to treat it as a software engineering project, not just as a coding exercise. We will start from a small console program and then evolve it into a server-backed simulation service with multiple sessions and a web UI. Along the way, we'll practice solid principles and design patterns such as strategy, factory method pattern, builder, observer, state, and adapter. All these patterns are going to be interweaved and will be a very important part of our architecture. The main point though is that this is about learning to structure code that can grow, not just to make little gliders on a grid. Alright, so what is Conway's Game of Life? If you have never seen it before, Conway's Game of Life is a cellular automaton. It is a visual simulation of living organisms that runs through generations based on some very simple rules. What we basically have is an infinite grid of cells or organisms, or in our implementation, a large finite grid. And each cell is either alive or dead. So as you can see, for example, here, that is a live cell, and here's a couple other ones. All the other cells within the grid are considered to be dead. So the idea behind the simulation is that time moves in discrete steps called generations. At each step, each cell looks at its 8 neighbors. We're going to be looking vertically, we're going to be looking diagonally, and we're going to be looking horizontally. That is going to give you all the neighbors of that one particular cell. So the idea basically is that at each step, each cell will look at its 8 neighbors, and it will decide whether to live or die in the next generation. So let's look at the 4 rules that basically drive this simulation from one generation to the other. Rule number 1 basically says that any live cell with fewer than 2 live neighbors dies because of underpopulation. So in the above example, if we have only 1 neighbor, then the middle cell is going to die because there is an underpopulation. The second rule is that any live cell with 2 or 3 live neighbors will survive. So for example, here we have 2 neighbors, and according to this rule, this cell would survive because it has exactly 2 neighbors. Then we have a third rule, which basically says that any live cell with more than 3 live neighbors will die because of overpopulation. An example here that you see is that we have 4 neighbors, which basically makes the cell in the middle die because of overpopulation. And the final rule deals with how do we get new cells or new organisms. And the idea is that any dead cell with exactly 3 live neighbors, so just like here, becomes alive because of reproduction. So this is what would happen in this particular rule. So the idea here of the whole simulation is that we go through all the cells in the grid and we apply these 4 rules to each cell, and then we render the result. And it's actually quite incredible, because believe it or not, what is amazing is that actually from these tiny 4 rules, you get beautiful patterns. Still lifes, oscillators, gliders that move across the board, even structures that can simulate computation. So here is an example of one such simulation running 40 by 40 grid with some sort of a random beginning. And as you can see, it's quite mesmerizing, it's quite incredible, and this is ultimately what we're going to architect in this series. All right, so let's talk about the end goal. What is it exactly, and how exactly are you going to learn things in these series? So the end goal here is basically to take you from a simple console program version of the game of life to a multi-session service. So we're going to do it in a number of stages. In stage 1, we're going to create a local console engine. We'll build a clean, solid implementation in Python with a text UI. This is where we'll focus on the domain model, like the grid, the cells, and the rules, and the core engine. This is going to be almost like a proof of concept. Then in stage 2, we're going to be extending the rules and the seeding. We're going to add multiple rule sets and multiple seeding strategies without rewriting the engine. This is where strategy and factory method patterns really shine. Next, in stage 3, we're going to use FastAPI backend and a remote engine. So what we're going to do is we're going to move the rules engine to a FastAPI backend, and the UI basically is going to talk to it via HTTP and web sockets. That is where the adapter and observer over the network will show up for us in the architecture. And finally, in stage 4, we're going to actually create a multi-session platform with a web UI. What we're going to do is we'll be able to support multiple simulations at once with the idea of one owner and multiple viewers watching the same grid. This is the beginning of a little simulation platform, and this is actually where it gets really exciting. So basically the idea here is that you're going to get both a hands-on console code and a taste of server plus web UI architecture. And I'll also mention here that the way that we're going to work in stage 4 is we're going to actually use a microservice to encapsulate our server. All right, so the question would of course now be, why S.O.L.I.D and why the design patterns? Well, first of all, let's have a look at S.O.L.I.D. Basically, we've got the SRP, OCP, LSP, ISP, and DIP. If you're not sure what these mean, again, as I mentioned before, there's a course that I have on all of those, but I'll explain them as we use them throughout this series. The design patterns, of course, the ones that we're going to use, are going to be strategy, factory method, builder, observer, state, and adapter. Of course, we could absolutely hack all of this into one giant game of life Python file. But you wouldn't learn much about architecting and scaling your code. In other words, is there really a need for all the S.O.L.I.D and design patterns? To actually make it work? No. To actually make it useful and extendable and maintainable? Absolutely. You want to create an architecture so that you could easily have your imagination move forward without having to rewrite all of your code every time you think of a new idea. When it comes to S.O.L.I.D, what exactly are we going to use? So we're going to use SRP, which is single responsibility principle. For example, grid only cares about cells in our architecture, and rules only care about transitions. In other words, each one of those classes, as you will see later on, is going to have a single responsibility. We also will have a game engine, which will orchestrate the grid and the rules. It will also have one responsibility, which is going to be the orchestration. Then we'll have OCP, which is the open and closed principle. And the idea here is that we'll add new rule sets and seeding strategies without modifying the core engine. When it comes to DIP, which is the dependency inversion principle, our UIs will depend on interfaces and ports and not concrete engines. And that is what lets us swap, for example, later on, a local engine for a remote one without actually having the UI necessarily change. That is actually very powerful. So what about the design patterns? We're going to be using strategy, factory method pattern, builder, observer, state, and adapter. Strategy is going to be used for rules and seeding. Factory method will be used to select the rules by name. So for example, we could use the classic Conway algorithm, or we can create a different one, which we call here highlife. We'll use builder for game configuration so that configuration doesn't explode into a messy constructor. We'll use an observer for grid updates to our UI. We're going to use state for simulation lifecycle, such as ready, running, paused, and stopped. Adapter will be used for plugging a local versus remote engine behind the same UI. So what you're going to see here is you will see each pattern in a genuine use and not as some sort of a toy animal example. As many times when you're being taught object-oriented programming, oftentimes you will see little examples about like dogs and cats, etc. Those examples are great when you want to explain a simple concept, but they're not really very good when you're trying to really get the kind of experience that you need in order to architect a larger system. So all of this will be explained carefully throughout our architecture and our code as we go through this series. Alright, so let's do a quick tour of our architecture. This is a UML diagram. We're going to obviously go through this in more detail, but let's do a quick tour of the classes that we're going to use. So we have the following main classes. We have the game configuration and the game config builder. We have the rules strategy, the Conway rules, and rules factory to deal with the rules in our game. We have the cell and the grid to actually build out the visuals. We have the game observer, game UI, and the rules engine port, which is a way of abstracting the UI from the actual games engine, if you will. Then we have also the simulation state plus the concrete state. So the simulation state could be like stopped or paused or running, for example, in an auto mode. We also have the most important ones, which are the game engine, the console UI, and the local engine adapter. So let's go a little bit more through the details of this. So in the core, the actual core of the application, we're going to have the grid, which is our 2D board of cells, and we'll have the rule strategy, which is the interface for the rule. And by interface, I mean it's an interface contract. Conway rules is one such implementation of the rules strategy, and we'll have other ones later on. This would allow us to plug in new rules into the game engine without actually changing the game engine. Then we have a rules factory, which creates a rules strategy by name. So this is our core. Next, we'll have the configuration classes. So we have the game config and the game config builder. And this is how we're going to bundle the configuration for an actual run. Next, we're going to have the classes that are responsible for the simulation, such as game engine, which is the heart of the simulation, and it uses grid and rules strategy to actually run the game. It has a state field that holds a simulation state, which would be ready, running, paused, or stopped. And this is how we would control, for example, how fast or what the actual game engine is doing. Now, the game engine knows a list of game observers and notifies them whenever a new generation is ready. So this is where you're going to see the split between what the engine does and how we actually render what the engine does. They're completely abstracted out. Next, we have the UI side, which is going to be the rules engine port, which is an interface for controlling the engine, like the start, the step, the pause. We also have a local engine adapter, which is an adapter that wraps a local game engine and implements the rules engine port. We also have a console UI, which is a UI that talks to the rules engine port and implements game observer so it gets the actual updates. Now, the most important thing here from all of this that you should see is that the UI itself does not know whether the engine is local or remote. It simply knows what we call a port interface. Port meaning how you communicate. That is what lets us being able to swap implementations later without having to rewrite the UI. So this is actually extremely powerful. Alright, so that was just a very quick little overview of the architecture, just a bit of a taste to give you. Next, let's have a look at the repo tour, which is the repository, and the 4 stages that we're talking about. First, let's quickly talk about the folder project structure. That's actually very important. Whenever you start a new project, you should think about how you're going to organize all your code. It's very easy to very quickly create code that becomes very difficult to maintain. So what we do first is we create a proper project structure. So basically, we're going to talk about the folder project structure. Now this is very important because whenever you have a project, you're going to be writing code, and when you write a lot of code, eventually it becomes very difficult to maintain unless you have a well-defined structure for your project. So this is what we're going to discuss right now. So here is a breakdown of our project. We have the parent directory, which is the GOL-project, which is our main project directory, and then you can see that we have two main subdirectories. The back end, which is going to hold all the information about the game engine, etc. And we also have a client, which is going to hold, for example, the web UI. So for stage 1 and 2, we will mostly work with config, which is where we're going to have the configuration objects and the game config builder. We're going to work with core, which is where the domain, such as the grids, the rules, the seating, and the port classes are going to be. We're going to also, of course, have the engine, which is going to be our game engine, which is going to be running the whole simulation. And we're going to have the UI, which is going to be specifically for the console UI and later other UIs as well. Now, the main_local.py is going to be the entry point for our console application. So the entry point is where everything is going to start. That's where it's going to bootstrap itself, and that's where it's going to load all the configuration and organize everything. Now, for later stages, the stages 3 and 4, we're also going to add, and as you've seen, I have color coded it here, we're going to add an infra directory, which is going to be basically like an infrastructure, which is going to be a simulation registry, which keeps track of multiple running simulations. We're going to also have a server directory, which is going to hold our FastAPI application with HTTP and WebSocket endpoints. And we're going to also have another specific subdirectory, which is going to be the client, which at first is going to be a simple HTML and some JavaScript web client that talks to the server, and later we're going to create a next.js client. The idea, of course, is that when you look at this, you should know where everything is living, so to speak. So we have a relatively well organized project structure. Now let's have a look quickly at the kind of starter code, which is going to be our main. So let me quickly just explain that to you. So this is the essence of the console program. We basically construct a game config via our builder. We then pass that into the game engine. We create a console UI and we subscribe it as an observer to the engine, and then we run the UI loop. Later on, for a server-backed version, the idea is the same, but instead of console UI subscribing directly to a local game engine, a web client subscribes to a WebSocket updates coming from the server. So if this kind of looks a little mysterious to you, I'm going to go through all of this, obviously in detail, as we're actually going to design all of this. But the idea here is, look how simple the kind of bootstrap code is. Very much a couple simple steps, which is build configuration, create the engine and the UI, get the observer pattern in action, and then hand over control to the UI loop, which basically loops over the simulation's generations. All right, so we are done with this first video lecture for this series. In the next lecture, we will do a proper architecture tour. Basically, we're going to go through the layers, the solid, and the patterns. We're going to go layer by layer, core, engine, UI, config, and infra, and map each class from the UML diagram to a real code file and discuss where the design patterns actually are used. So I'm going to see you in the next video, and as always, keep on coding. See you soon.